Hi everyone, this is your struggling CS student, and I've just solved the problem of the day. It's quite easy, so I'm going to solve a random question and see how it goes. All about their grind set. Okay, looks like we have a graph problem. It's been a while since I did a graph problem, so that's good. So we have a maze. It's a medium quant problem. There's no editorial, and it's also a premium problem. So the random question is 2077 path in maze that lead to the same room. Directed graph as well, and undirected graph. It seems interesting. So a maze consists of n rooms numbered from 1 to n, and some rooms are connected by corridors. You're given a 2-day integer array corridors where corridors of y connects room 1 to room 2 and indicates that, yeah, okay, allowing a person to go from room 1 to room 2 and vice versa. So it's undirected edge. The designer of the maze wants to know how confusing the maze is. The confusion score of the maze is the number of different cycles of length 3. For example, 1 to 2 to 3 to 1 is length 3, but 1 to 2 to 3 to 4, and 1 to 2 to 3 to 2 to 1 is not. Okay. 1 to 2 to 3 to 2 to 1. Let's see. 1 to 2 to 3 to 2 to 1. Oh. 1 to 3 to 2 to 1 is not, because it's only a cycle of length 2. 1, 2, 3, 4 is not a cycle. 1, 2, 3, 1, this is a cycle. Okay, so two cycles are considered different if one or more of the rooms visited in the first cycle is not in the second cycle. Return the confusion score of the maze. This question seems kind of hard for medium. Oh my god, okay. Two cycles are considered to be different if one or more of the rooms visited in the first cycle is not in the second cycle. Okay, so they have to be like mutually exclusive. Is that what it means? The cycles are different if one of the rooms visited. Yeah, I think it's mutually exclusive, right? Okay. There are two. One cycle of length 3 is denoted in red. And is up to 1,000, and corridor start length is up to 5,000. Or is this 50,000? 50,000 is 10 to the power 1, 2, 3. Yeah. There are no duplicate corridors. This question seems kind of hard. I don't even have a clue on how to begin. But let's see. Let's take a look at example 1, right? How would we derive the answer? So you have like 5 to 2 to 1, 3, 4. Okay. 1, 3, 4. 1 to 2, 5 to 2, 4, 1, 2, 4, 4, 1, 2, 4, 3, 1, 3, 4, 3, 1, 3, 4. One way I'm thinking of, but I'm not sure if it will work, is basically we try to brute force it, right? So there are only n number of rooms. Okay, there's only n number of rooms. We can do like a depth first search for every single room on every single edge, but we only traverse 3 levels deep. We only go 3 levels deep. So let's say starting from room 1, we go through all the edges. So we go here, we go here, we go here. After 3 steps, we see, hey, have we reached the starting point? If so, okay, we increment like cycle plus equals 1. Right, increment it by 1, then we backtrack from there. Oh, we backtrack from there. Then we say, okay, we go here, depth for search. This is not equals to the original node that we started, so we're done. Okay, that means we have explored this path, this path. There's no more paths going up from here. We'll backtrack, we'll backtrack. Okay, then we mark this node as done. This node is done. Then we say, okay, what about this one? Right, go here, go here, we go here. Oh shit. What if you have a connecting point like this? Because the reason I hesitated is because yeah, if you go here and you go here and you go here, you get one cycle, right? But then it's part of the same cycle. So I was wondering, if let's say after we have finished a particular node, like we finish this, do we still need to traverse another node that's part of the same cycle? That's part of the cycle. So suppose you have this connection here like that. 2 cycles are considered to be different if one or more of the rooms visited in the first cycle is not in the So what would the answer be here? If like there's a corridor connecting from 2 to 3. So you have like one cycle like this. You have another cycle like this. I guess this is 1 and this is 1. So answer is 4. Okay. 2 cycles are different if one or more of the rooms visited in the first cycle. Oh shit. Okay, okay. I understand now. It's not that 2 cycles have to be mutually exclusive, but as long as in the cycle of length 3, as long as you have one of the rooms that are different, then it's considered as a different cycle. Oh, okay. So what it means is if there's an edge connecting like this, that means that this is one cycle, but this is also another cycle. This is also another cycle, another cycle. Ooh. I mean, it's not that bad, is it? How will we check if 2 cycles are different? That's the tricky part, right? So if we go here, and we go here, and we go here, right? I guess we can do like, we can normalize. We can normalize the cycle. So in this case, this like, for example, when we finish reversing one, we have added one cycle, right? So the cycle will be like 1 to 3 to 4. We'll normalize it by sorting it, so we'll store it like 1 3 4, like so. So when we go from 3 again, when we start from 3, right, we go 3 1 4 3 1 4 3, right? Oh, I guess I have to do like this. So do like this. So 3 1 4 3. Oh snap! No, we can't add the 3 here, so we can't add the 1 here as well. So in this case, we will store the cycle like this, right? We will sort this. Sort this is 1, 3, 4. We notice that 1, 3, 4 is already part of the cycle that we've already seen. Then we will not count that. We will not count that. So the 2 cycles here will be like 1, 1, 2, 4, and 1, 3, 4. Yep. Hey, hold on a second. Maybe it doesn't have to be so complicated. Now I'm thinking of like an alternative approach. Okay, let's see if the alternative approach works. If it works, then we'll go with the alternative approach. If not, we'll try this brute force method. So what's the alternative approach? The alternative approach is to consider two pairs of nodes that are neighbors. Right? So we say, okay, we say for every pair of nodes, if they are a neighbor and they have another common neighbor, then we can store like the normalized, I guess, the ID of the cycle. So for example, if we take 1, we take 2, right? Then we say, now what are your neighbors and what are your neighbors? 1 has a neighbor of 4 and 3, right? 2 has a neighbor of 5 and 4. Now, because these 2 pairs of neighbors are connected, any common neighbor that you have will be part of the cycle. Now, how do you do that check quickly? Because like if you iterate through every pair of neighbors, that is n squared. Yep, that's n squared. And then if you do another check here, like so, if you check each and every neighbor, that's going to be like n cubed or something, right? So 1, the neighbor will be 2, 2, 3, 4. For 2, the neighbors are 1, 4, 5, 1, 4, 5. So this pair of neighbors, you look at their. Wait, what is corridors dot length? Corridors dot length. Oh my god, it's so big. It's freaking 50,000, man. I was thinking maybe we just need to look at every pair of corridors. Like so, like every pair of corridors. Even if you keep this sorted, you still have to track like this. Be like this, compare it like this, compare it like this, compare it like this. The worst case is still, even if it's sorted, it will be n log n though. You need to check one at a time, do a log n search here. It's like n squared times n log n. That's horrible. Wait a minute. No, we don't have to iterate through n itself. We can iterate through corridors dot length. Alright, corridors dot length. So for that's every pair. That's every pair. So we get their neighbors, iterate through. So that would be like n, where n is the length of corridors, times, well, what's the worst case? Worst case is we need to iterate through all of its neighbors. Now let's say n log whatever the length of this is. I don't know. This could be n, and it would be n squared log n. N squared log n. It's a bit scuffed because this is no, actually it's more like, let's say C is corridors dot length times n log n. Yeah, that would be the time complexity. If we iterate through every corridor, so every corridor is a pair of rooms. We take the we iterate through the list of neighbors for a particular node, right? And we compare against the other list. And we search for a number that matches. So if it matches, could you have more than one match? Is it possible to have more than one match? Yeah, no duplicate corridors, okay. Now, is it possible for one to be connected to five? That's the question. Actually, technically you can. So if one is connected to five, then oh shit, then it wouldn't be n. It wouldn't be c times n log n. Because after we find one, we still have to find the next one. Okay? No, that is still n. That is still log n. Actually, what's the time complexity of set intersection? Set intersection. So how will I do the set intersection? Probably add everything here into a set. Then we iterate through this again. Right, iterate through this again. And we say, hey, is this inside here? If it is, it forms a, so we don't have to do a log n search. We just, use more memory to maintain a set of corridors we've already seen in one of the neighbors. Iterate through the other list. Anything they have in common must form a cycle of length 3. So in that case, the time complexity would be like c times n. Would that be fast enough? C times n. I don't think it is actually, because like it's like what, 50,000 times 1,000. That'd be 50, 1, 2, 3, 1, 2, 3. This is 50 million. Maybe it's fast enough. It could be, because in LeetCode, the maximum number of operations usually it's 100 million. Let's try the approach. Let's just try it. How will I do this? So for A, B in corridors, we're gonna get their neighbors. So we probably have to build the graph first. So we say graph is equals to node for node in range of 1 to n plus 1. Then we build the graph. For a corridors, we say graph of A dot append B, graph of B dot append A. Okay, now we build the graph. Then we say do the same thing here. Count equals to 0. Not sure if we need to keep track of the different number of I'm not sure if we need to normalize the set IDs, right? So let's say I'm at 4 and 2. Yeah, I think we need to normalize the set IDs, which makes it even more painful. For A and B, maybe dot add is better. This is set, because like you never have duplicate edges, and then we can easily perform set intersection operation if we map it to a set. Guess we can just print graph of A dot intersection of graph of B, just to take a look. So like 4 to 3. Oof. Minute 4. This is what they have in common. That's because we count them twice, right? We count them twice. Like some of it is counted more than once. Okay, great. So we would say like cycle is equals to this. Cycle. So this is what they have in common, right? What they have in common. So for node in cycle, right? Cycles dot append. Okay, this is common. For not in common, we say cycle is equals to AB. Nope. Sorted. Okay, fine, sorted. But this would be a list converted into a tuple. Then we do cycles dot add cycle. Okay, it's correct, but I do not know if the term complexity is good enough, right? Because this is the term complexity is OC, where C is the corridors dot length. Graph, this one takes ON time to build, so it's N plus C, plus C times N, because like I do not know how, like this intersection probably takes ON time. I think some of the cases are impossible. Which make this operation fast enough. What do I mean by that? So, yeah, maybe I do not want to erase all my working. So suppose you have a room which is like 1 is connected to 2, like a room that's connected to every other room, right? Like think about the worst case. think a key thing to realize is that there are no duplicate corridors. Where is it? There are no duplicate corridors. Okay. So it will be like this, like this, like this. 4 is connected to 2 as well. So 2 is connected to 1, connected to 3, connected to 4, connected to 5. 1 is connected to everything, 2 is connected everything, 3 is not connected to 5, 4 is connected to everything, and 5 is connected to everything. In some cases really impossible, maybe not. So 1 maps to 2, 3, 4. 2 maps to 3, 4, 5, right? 1, 2. This is 5. This is 1, 2, 3, 4, 5. 3 maps to 1, 2, 4, 5. 4 maps to 1, 2, 3, 5. Ooh, actually, it's still pretty bad, to be honest. It's still pretty bad. No, 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 yeah. Yeah, C times N. Let's see if it passes. This is kind of like brute force C. Oh, it got accepted. So I'm very happy that it got accepted. This is kind of brute force C. But yeah, the complexity here is C times N. I'm not sure because of like uh uh the test cases are like not strong enough. But yeah, this code works. It's relatively short. It's quite clean as well, but definitely took me some time to think about it. I'm not sure if this is optimal, to be honest. I'm not sure if this is the right way to solve it. If the path starts at I, what properties must the other two rooms in the cycle have? The other two rooms must be connected to room I and must be connected to each other. I don't know what the hint is trying to say, to be honest. Let's see some solutions. Yeah, I did set intersection, which is like brute force. This is an n-cube solution for sure. Set intersection of node pairs. This is what I did. You build the graph. Yep. TFS. Is this the one that I just saw? Is C is your edges. C times uh C times N. This is C times N. This is up to N as well. Yeah, so it's C times N. Analyze complexity. N times N plus M squared. This is n plus c, n plus c, and then this is c times n, and this is also up to n. Let's see this one. Oh, Vlad, nice. Yeah, but I think Vlad is like quite a respected member of the community. So okay, so the key to avoiding duplicate cycles and visiting each node again is to traverse the node in increasing order. Ah, okay. After identify 3 nodes, we check if there's a connection between the first and the last node to count it as a loop. With this, we can write the DFS solution. However, since we only need to check the triplets, 3 loops will do. I tried a few container options for edges, adjacency list, backed by a hash set. Okay. What's the fastest for Python and a Boolean adjacency matrix for C++? Adjacency list and result. Okay, initialize your adjacency list. Result of 0. The min. Wait, why we do this? I think it's because of the traversal. Okay, fine. Time complexity. Ah, come on, man. Time complexity NQ. Really? Oh, let's ask ChatGPT. I'll do it later. It's n times c, right? I mean c is c times n. Okay, the reason why this is like constant time is because you are only sorting 3 nodes. Then you're just keeping track of the cycles. Well, anyway, that's it for me for this question. Paths and maze that live in the same room, 2077. So thanks for watching. This is my code once again, and have a great one.